Good morning, Year 7s. Well done for clicking on this video first of all. I hope you've had a lovely half term. So for today's lesson, I thought I'll do something a bit different and actually show my face because I do really miss being in school and teaching you and talking to you. So this way, I can still talk to you and I know you're watching from the other side. So in this video I wanted to just go over what we've started just before half term, which is gas pressure and pressure on solids. So just like any other lesson, we need to start with a do now quiz. So I'm going to give you 5 minutes to answer these 5 questions. So question number 1 is drawing the particle model for solid, liquids and gases. Question number 2 is describing the motion and the arrangement in solid, liquid and gases. Question 3 is defining the boiling point. Question 4, describe what happens to gases as temperatures increasing. And question number 5 is recalling the equation for pressure, which we have done 2 weeks ago. Okay, so go, 5 minutes. Two more minutes left, so if you're already finished, just skip to the next part. Okay, so time's up. Okay, so here we've got the particle model of a solid. So we know solids are arranged in nice neat rows and they are touching. And the motion is that they are vibrating on a fixed position just like this. Obviously all of them are vibrating, but I don't have enough fingers to do that. Okay, so in liquids, the particles are arranged more random, but they're still touching and they are flowing over each other like this. So this would be the movement of liquids. Okay, so lastly we've got the particle model of gases, and for this I've used the jar. So at the moment like this, it looks like it's a liquid in the jar at the bottom and the particles are just flowing around each other, but if they have enough energy, the particles will start to gain more kinetic energy and therefore become a gas or turn into a gas, and that will look something like this. Okay, so the particles in gases, they are moving randomly. They're not touching unless they are colliding like this, but usually they are free from any other particles. And the more energy the gas particles get, the faster they will move. So the more kinetic energy they will gain. And obviously we can do this by heating the particles up. The more energy we put in, the more kinetic energy they will gain, and the faster they will move. And the more energy they do have, the more they will collide against the container. Okay, obviously this jar is a solid surface and the particles are bumping against it. So what do you think is going to happen if this was a stretchy material? Okay, have a little think to yourself. What do you think would happen if the pressure increased and the surface was stretchy, like a rubber material? Any idea yet? So if the pressure increased and the surface was an elastic material, then it would expand just like this balloon did. Okay, so I was blowing in more gas particles and the gas particles made the balloon expand. And I'm going to show you a demonstration just now, so let me blow up 2 more balloons. Okay, so we've got Bob and we've got Jess. Okay, Bob and Jess are going to go in the fridge. So what do you think is going to happen to gas particles when they're being cooled down? Okay, so think about the motion and about kinetic energy. And once you've answered that, think about what's going to happen to the balloon when it is in the fridge. Do you think it's going to expand? Do you think it's going to shrink? You tell me. To figure this out and to make it more scientific, I'm going to measure the circumference of both of these balloons, and I don't actually have a measuring tape, so I have to be creative here. So I've got a piece of string and I drew a line where I'm going to measure the circumference from, so it's going to be the same spot after I take them back out of the fridge. And I'm going to put this around the balloon, and that's how long it is. So now we can use a ruler to measure the circumference, and I'm going to write that down. Okay, so I'm using my ruler to measure the length of this. And I've actually decided one's going in the fridge, one's going in the freezer to see the 2 differences, whether it makes a difference. Okay, so let's go in the kitchen. Okay, Bob's in the fridge. There we go. Just about fits in. Okay, so it's almost 10 to 2 and we are going to check on the balloons in about an hour or 2. Okay, so you probably already know from the previous lessons that we've done that pressure is the amount of force applied over a specific surface area, okay? And that's shown in this equation here. So I've got my balloon here and I'm going to apply some force onto the balloon like this, okay? And that makes the balloon move. What do you think is going to happen if I decrease the surface area? So the surface area by which I'm applying the force is the tip of my finger. So what if I use something with a much smaller surface area, such as this needle, okay? So if I apply the same amount of force with a smaller surface area, poor balloon's gonna suffer, isn't it? So there we go. Obviously this can be applied to other scenarios that I'm going to explain right now. So the example I wanted to talk about is about us walking on the floor. So obviously all of us have got a mass, and we can work out our weight, which is the force, by calculating our mass times the gravitational field strength, which is something we've already done in a previous topic, if you remember. And this force is acting on the floor, and since it's our feet that we walk with and the feet are touching the floor, that's the surface area that is that the force is being exerted on. Okay, so if you're walking with shoes, the surface area is bigger compared to if you are, for example, just like in this video, dancing on point shoes, because the surface area of the point shoes is much smaller. And I've used a notebook to trace around my feet, so the shoes and the point shoes, to show you the difference in surface area. Obviously this isn't as neat as I wanted it to be. It's very hard to do it with one hand while holding a camera, but you can see that the surface area when I was wearing my shoe is much bigger compared to when I was wearing the ballet shoe. And my weight hasn't changed, so my weight is still the same. And if you know, weight is the force that someone is exerting. And when I was wearing the ballet shoe, I was exerting all of that force in this small surface area. So imagine someone was stood on your hand wearing this shoe. That would really hurt. But if someone stood on your hand wearing these shoes, it wouldn't hurt as much, because all of the force is evenly distributed all over this whole area. Okay? Okay, we know that the force is being measured in newtons, which is N, and the surface area is measured in meters squared. So the unit for pressure is Newton per meter squared, and it's also known as Pascal. So a Pascal is the same as Newton per meter squared. And if we are using different units, for example, so we can use kilonewtons and centimeters squared instead, that's not Pascal anymore, but we can still use that, but we just need to change the units to make sure it matches up with the original values that we are given. So we're going to do a few practice questions using this equation and knowing how to rearrange it as well. Okay, so we're going to do this question together. So Mr. Dakin weighs 1,000 newtons and is wearing stiletto heels, which together have an area of 0.0001 meters squared. What pressure does he exert? So we've got the equation here, so all we need to do is put the numbers in. I'm going to write out the equation again because it's going to be useful for you as well to get into the habit of writing the equation down so that you remember it. Okay, so and the force is 1,000 newtons divided by the area, which is 0.0001 meters squared. And that together will give us 10 million Newton per meter squared. Okay, so that would be the answer to that question. Right, so have a go at question 2 and 3 on your own. So this is the one we've just done together. And again, I'm going to just highlight the values given to you, and this is for question 3. So pause the video here for 2 minutes and do this on your own. This next question is a bit trickier because we have to use 2 equations, but it's still easy because we have done the equation before in a previous topic. So Mr. Wilson gets onto the moon. The gravitational field G on the moon is 5.5 newtons per kilogram, and his mass is 75 kilograms, and his surface area is 0.008 meters squared. So question A is asking us, what is his weight? So his weight can be calculated using this equation here. So for 2A, we've got weight equals mass times G, and I know the mass that's not it. We know the mass is 75 kilogram, so that's 75 kilogram times by the gravitational field strength, which is 5.5 newtons per kilogram. We multiply that together, we get 412.5 newtons. So newtons, remember, is a force, weight is a force. So for part B then, we are going to calculate the pressure that Mr. Wilson exerts onto the moon. And to calculate the pressure, we will be using this equation up here. And that is pressure equals force divided by area. And I know the force, which is 412.5 newtons times, nope, not times, divided by the area, which is 0.008. And when we divide those two numbers together, we get 51,562.5 newtons per meters squared. Okay, so it was a two-step process to find the pressure of Mr. Wilson on the moon, because we needed to find his weight first. So question 2C is asking you, what pressure would Mr. Wilson exert on the Earth? And the Earth has got a different gravitational field strength, which is shown here. So I want you to use the same method of finding his weight on Earth first by using the weight equals m times g equation, and then calculate the pressure using the force that you've just calculated and dividing it by his surface area. So I'm going to give you 2 minutes again, so pause the video, time 2 minutes, and I'll give you the answer in tomorrow's lesson. So it's actually the next day now, and I've taken the balloons out of the fridge, and I'm going to quickly measure their circumference. You have to act quickly, because otherwise the gases are going to gain more energy, because you're taking them out of a cool environment back into a warmer environment, which means that the gas particles will gain more kinetic energy and therefore inflate the balloons. Gas pressure is really important for everyday situations. So if you think about it, if you're riding your bike, for example, and it's a very hot day, the tyres will be more inflated, or will feel more inflated, because it's hot outside, gas particles are gaining kinetic energy and are colliding with the inside surface of the tyre much more frequently. Therefore the pressure inside of the tyre increases, and it feels a lot harder. However, if it's a very cold day, then the tyres will feel softer, because again gas particles will have less kinetic energy, will collide less with the inside surface of the tyre, and the pressure will decrease inside it. And that's the same for car tyres as well. So it's really important to keep the pressure right in car tyres, otherwise road accidents can happen. So pressure is really important. And another example for biology would be pressure in your lungs. So because of the pressure difference of the outside and inside of our lungs, we can breathe our air in and out. But you will learn more about this in year 9. So make sure you remember what pressure is, how to calculate it, and relate it to the particle model that we've been talking about since day 1 of secondary school, okay? And lastly, there is a quiz on ePraise that I need everyone to complete, just to check whether you understood how to calculate pressure, okay? It was nice speaking to you through the camera, and I'll speak to you again soon. Bye.